After studying this module, you shall be able to know what is internal ballistic, learn different phenomena of internal ballistic, identify how combustion take place inside the bore of the weapon. Introduction. The term ballistic is derived from the Latin word ballista, which referred to a crossbow like device for throwing some stone by means of twisted ropes. In order to understand element of ballistic, it is divided into three parts, as number one is internal ballistic, second is external ballistic, and the third one is terminal ballistic. Internal ballistic is the study which deals with the motion of projectile in bore of the weapon, whereas external ballistic deals with the flight from the muzzle of the weapon to the target. This indeed is terribly complicated subject involving parameters such as shape of the bullet, sectional density, atmospheric conclusions, and even rotation of the earth in larger caliber weapons. With the advent of powerful personal computer, the complex calculations have become quick and accurate. The terminal ballistic deals with the behavior of missile once it reaches the target, such as wounding capability, and include its performance in water, soil, brick, concrete, wood, and other bullet resistant materials. In order to understand the factors affecting the projectile in the barrel, certain terms need to be explained, such as smoothbore weapons, rifled firearm, lock time, ignition times, and barrel time, etc. Internal ballistic, which deals with the motion of projectiles, commences as soon as the first grain of the propellant is ignited and subsists till projectile leave the muzzle end of the weapon. The study includes all the details concerning the impulse, which makes the projectile move out from the muzzle in the air. As a matter of fact, a projectile obtains its energy during the period it remains in the firearm. This period can be divided under the three main heads. Number one is lock time, ignition time, and barrel time.
Let us know about them in detail. First is lock time. It is the time interval between release of sear and the impact of the striker on the percussion cap. A short time interval is advantageous in case of rapid fire. The lock time can be measured in a number of ways. In one such system, the use of linear motion sensors and an oscilloscope is made. Next is ignition time. It is the duration or interval between the striking of the firing pin to blow the ignition of the first grain of powder. The ignition under the normal conditions takes place at an interval of about 0.002 seconds. Next is barrel time. It is the time interval from pressing of trigger to the exit of the bullet from the muzzle end. In case of most weapons, it is the lock time plus ignition time plus barrel time, which varies from 0.003 to 0.007 seconds. Now, let us learn about the phenomena of internal ballistics. Internal ballistics includes study of several phenomena, some of which are as follows, would be discussed in two parts, that is, internal ballistics part 1 and internal ballistics part 2. Let us learn about them. Ignition, burning of propellants and geometry of gunpowder, pressure and its measurement, atmospheric conditions like temperature, shape of cartridges, density of loading, twist of rifling, bullet fit and velocity of bullet at muzzle, heat generation and problems, strength of barrel, erosion, corrosion or rusting of barrel, bullet of the weapon, recoil of the weapon, and phenomena of bursting of barrel. Now let us discuss about them in detail. First is ignition. When the firing pin strikes the hammer, the priming compound explodes with great velocity, causing jet of flames of an extremely high temperature to pass through the flash hole into propellant chamber. This jet of flame with a temperature of about 2000 degrees Celsius ignites the propellant, which burns at high speed to form a large volume of high pressure gas, which accelerates the bullet down the barrel and out of the muzzle end. Next is burning of propellant. Nitrocellulose propellants, if ignited in an unconfined space, will burn gently. The heat and the pressure built will accelerate the rate of burning exponentially if it is in a confined space. The products of combustion in case of nitroglycerin are nitroglycerin is equal to the carbon dioxide plus water vapors plus oxides of nitrogen plus nitrogen and the heat. 1 gram of nitroglycerin will produce 1000 cubic centimeters of gases at normal temperature, that is 0 degrees Celsius, and pressure 760 mm. The heat given by the reaction is also tremendous but 1000 calories. The temperature may cross 3000 degrees Celsius. Only a portion of this energy is converted into kinetic energy of the projectile. Most of it is wasted. In a weapon, the projectile is confined in a cartridge case, the mouth of which is closed with a bullet. The round of ammunition is then supported by the chamber walls and the standing breech of the weapon. Under these conditions, the pressure built up will continue until it is sufficient to overcome the inertia of the bullet and starts its acceleration down the bore. The heavier the bullet, greater will be the resistance and higher the pressure. When the propellant burns, it gives rise to gases and they remain confined completely within the cartridge case, and pressure is exerted equally on the base of the cartridge, its wall, and the base of the bullet. Once the bullet starts to move, the volume filled by the gases increases and the pressure starts to fall in accordance with the gas laws. In modern propellants, moderating the propellant grains can compensate this fall in the pressure. This modernization involves the addition of grains. In some propellants, the grains are also pierced with holes. There are different types of powders, namely progressive powders, digressive powders, and constant burning propellants, which are explained further. First is progressive powder. For some weapons, particularly in respect of shoulder arms, it is desirable that pressure should not develop suddenly, and the increase in pressure should be gradual. Dense and the bulk powder, when ignited, burns rapidly, with the result that the projectiles receive a big push. Gradual development of pressure not only provides better velocities but also prevent quick wearing out of the barrel. Progressive powders are manufactured to suit the needs of a particular weapon by controlling the shape and size of powder grains. For example, powder grains having multiple perforations. Next is digressive powder. In the case of digressive powders, the shape and the size of grains are kept such that as burning of propellant progresses, the rate of burning goes on decreasing. For example, non-perforated powder grains. Next is constant burning of propellant. In this type of propellant, the powder grains contain a single perforation and the total surface area of burning at any instant is constant. For example, single perforated grains. The modernization of the propellant grains no doubt has an effect on changing the rate of burning as the propellants are consumed. As a result of this, the internal pressure does not drop so drastically once the bullet begins to move. The moderation of the propellant has to be carefully regulated to ensure that they are totally consumed just before the bullet reaches the end of the barrel. Any propellant which is not consumed before the bullet exits the barrel will result not only in low efficiency rate for the cartridge but will also produce a large muzzle flash which can be extremely disconcerting when firing at night as it has the effect of destroying the shooter's night vision. Next is geometry of gunpowder. Burning of propellant is a function of geometry of gunpowder. Certain terms concerning burning are explained further. First is combustion. Take place when the reaction of the burning propellant or substance arise out of its contact with the air in an open space. If The reaction takes place in an enclosed space. The space should be larger enough for the heat generated to be dissipated, and the gases produced will disperse without generating any significant increase in the pressure. The spreading of fire is brought out by gradual heating of the surrounding area. Next is deflagration. It includes rapid and violent burning and is intermediary step between gradual combustion and detonation. This is caused by the acceleration due to gradual heating up or by the increased pressure of the gases produced by decomposition of the mass according to conditions prevailing in the explosive system. Next is detonation. It takes place when the explosion is extremely rapid and the formation of gases is almost instantaneous, transmitting shock waves, which are also known as explosive waves. Ballistic powders are capable of producing large volumes of high temperature gases in a very short time by means of deflagration. The propellant charge is composed of quantity of grains that are ideally of the same shape and size. Solid cylindrical grains present smaller area as burning progresses. Cylinders with certain perforations along their length presents nearly a constant surface, and propellants of this shape are called as constant burning propellant. With multiple perforations, the amount of propellant burned increases as burning progresses. In forensic term, ballistic advantage of the latter is that it generates gas at a lower rate initially when the total volume behind the projectile is small and produces gas at an accelerated rate as the projectile gathers velocity and creates greater volume behind as it moves through the barrel towards the muzzle to escape in air. Next is combustion of propellants and barrel length. There are wide variations in the rate of burning of the powders. Some powders burn quickly while other burns slowly. Various firearms require different burning rates. For example, in pistols and revolvers, a very quick burning powder is needed so that the powder is converted into gases before the projectile is pushed out of the short barrel of the firearm. If slow burning powder is used, the projectile will not acquire the desired velocity. Likewise, if quick burning powder is used in long barreled firearms, the projectile will not receive sustained pressure. Consequently, for the maximum pressure, the projectile will have a lower velocity. If a powder with appropriate burning rate is used, the projectile can be given higher velocities for the same maximum pressure. The rate of burning has to be related to the length of the barrel. The pressure in the firearm cannot be increased beyond a certain limit, and the limit is determined by mainly the strength of the barrel and action of the firearm to withstand the pressure. Next is atmospheric temperature. The ammunition is manufactured to give the desired velocities and pressures at a particular atmospheric temperature. If the temperature differs only slightly at the place of the use, the ballistic aspects are not seriously affected. If temperature variations are substantial, example in Ladakh or in Rajasthan desert, they affect the ballistics aspects of the ammunition. In hot places, the pressures developed by excessive and the firearm may burst. In cold places, the ammunition may develop low velocities. Indian Accordance factories manufacture most of their ammunition with a temperature tolerance of 52 degrees Celsius to 72 degrees Celsius. It has been found that the variation in the velocities because of the temperature is about 1 meter per second per degree centigrade. Next, we will learn about the shape of the cartridge case. It has been observed that if there is an abrupt junction of the neck and the case, the rounds develop greater pressure for the same quantity of powder. The combustion is more uniform. It appears that abrupt neck joint deflects the hot gases inward. The hot gases quickly ignite the powder charge in every nook and corner. Thus, correct initiation and complete combustion of the powder charge takes place inside the cartridge. It reduces excessive heating and wear and tear of the barrel. Next is heat problems and combustion of propellant. During the combustion of propellants, the temperature often reaches to 3000 degrees Celsius. The steel barrels of the firearm easily melt at these temperatures. If gases at this temperature remain in the barrel for any appreciable time but Fortunately, the time for which the hot gases are in contact with the barrel is about 0.001 second. Therefore, the high temperature does not create the havoc which is otherwise expected. Instead, there is a gradual erosion called washing of the barrel due to continued flow of the hot gases. They carry away metal slowly but surely. Both the aim and the range are considerably affected by the increase in the diameter. The repeating firearms, that is, automatic or semi automatic, are eroded more quickly. In these, the barrels do not get sufficient time between the shots to get cooled. The erosion at higher temperatures is greater. The use of nitroglycerin powders, which result in higher temperatures, wear out the barrel more quickly. The lead of the barrel is the first part to be affected in the firearm. A widened lead greatly affects the accuracy of the projectile. It facilitates the escape of the gases and consequently a portion of the energy is wasted. Gas cutting is another phenomena observed in extensively used firearms. The outrushing hot gases at certain points, either due to some deformity in the projectiles or erosion of the lead, come out in the form of jets, which create furrows. These furrows attain greater width and depth with the passage of time due to the ever increasing volumes of gases rushing through these channels. Next, we will learn about the density of loading and combustion rate. Load density is the percentage of the space in the cartridge case that is filled with powder. In general, loads close to 100% density or even loads where sitting the bullet in the case comprises the powder, ignite and burn more consistently than lower density loads. In cartridge surviving from black powder era, the case is much larger than is needed to hold the maximum charge of high density smokeless powder. The extra room allows the powder to shift in the case, peeling up near the front or back of the case and potentially causing significant variations in burning rate. As powder near the rear of the case will ignite rapidly, but powder near the front of the case will ignite later. This change has less impact with the fast powders. Such high capacity, low density cartridges generally deliver best accuracy with the fastest appropriate powder, although this keeps the total energy low due to the sharp high pressure peak. An important factor which affects the rate of combustion is the density of propellant load. Density of propellant loading is given by the formula S, which is the density of loading, capital V, which is the volume of cartridge case, and mu, which is the volume occupied by powder, into 100. In rifle cartridge, the loading density varies from 75 to 95. Higher densities are more useful as they permit uniform burning, proper development of pressure, economical, and give rise to regular velocities. When loading density is small, it may result in giving hang fire. Improper loading density materially affects the range and aim of a shot.
Summary. Internal ballistic is the study which deals with the motion of projectile in the bore of the weapon. Lock time is the time interval between the release of the sear and the impact of the striker on the percussion cap. Ignition time is the duration or interval between the striking of the firing pin to bow the ignition of the first grain of the powder. The barrel time is the time interval from pressing of the trigger to the exit of the bullet from the muzzle end. There are different types of modern propellant, namely progressive powder, digressive powder, and constant burning propellant. There are different factors which affect the combustion rate of the propellant, such as barrel length, atmospheric pressure, density of loading, shape of cartridge, etc.